Alright, nice. So this is note 8 in CS70, and this one is going to cover polynomials. So the key purpose of polynomials, at least the way we're going to use it in this class, is to kind of take what we already know about polynomials over the real and complex numbers and then apply it to modular arithmetic. So I'm sure we're all fairly familiar with it, but just to kind of, start out with some definitions. So we have these polynomials, and they're of the form, some coefficient, ad through a0, times some variable x to the power d, or degree d. And yeah, that's basically the largest exponent, and it'll sort of make more sense when we look at an example, but you can just visualize x squared plus 2x plus 1, for example. That would have an ad of 0, that would have an ad minus 1 of 2, and then its a0 would be 1, and then similarly its d would be 2. That's the degree of its highest variable. Anyways, I'm sure we know what a root is. This image does a good job of sort of defining that. A root is anywhere where any x value such that we input that into a function and our output is 0. So if we plug in 2 into this function, then we'll get 0. If we plug in -2 to this function, we'll also get 0, right? I'm sure we've all seen this before. And two properties that we're going to deal with in this note that is really going to help us, especially in the mod space, are these two. And the first one states that a non-zero polynomial of degree d has at most d roots. So, for example, take a polynomial of degree 1. We can see that at most it can intercept the x-axis just once. It's also possible that it is just a horizontal line. So a non-zero polynomial of degree d, yeah, this technically has degree 0, so that's why it has 0 roots, right? Because this is just like y equals 3, for example. Okay, and this other property, which is more interesting, is given d plus 1 pairs, so one more pair than our degree, such that all of the x values are distinct, there's going to be a polynomial p of x of degree d such that it goes through every d plus 1 point, all d plus 1 points. And that's going to be a unique polynomial we'll see. So for example, we have a polynomial of degree 1, but we need degree plus 1 pairs to create this polynomial, so we need 2 pairs. Here we have 1, 1 and 2, 3, and those pairs allow us to create this polynomial. Okay, so the next topic is going to be on polynomial interpolation, and we're going to start off by summing up what property 2 told us, which was, again, we need one more than our degree points in order to create a degree d polynomial. So if we have a degree 1 polynomial, we need 2 points. If we have a degree 2 polynomial, we need 3 points, etc. And so we're going to use this property to kind of show how we would create our unique polynomial given the d plus 1 pairs. So again, we need d plus 1 pairs to make a polynomial of degree d. And just for example's sake, we're going to say that, and this should actually be, we're going to assume in our d plus 1 pairs that in the first pair, the y value is going to be equal to 1, right? But in every other pair, pairs I equals 2 through d plus 1, all of those pairs are going to have y equal to 0. And that means that we can construct this other polynomial, we'll call it q of x, where it's basically x times all of its, these are technically all roots, right? Because if we pass in, say, xi of or say x2 for example, it's going to zero out this polynomial here. And yeah, again, so for all xi's, it's going to equal 0 for as long as the I is at least 2 or up to d plus 1. But as you can see, because x of 1 is not included in that range, it's going to actually give us some non-zero constant. And from there, we can take, we're going to see that our polynomial that we want to find is going to be q of x divided by q of x evaluated at the first pair. And so we can sort of give an example using these points. I'm actually not going to do that right now, but if you look in the notes, you can see a pretty nice visual of how they do this. I mean, I can verbally talk over it. So clearly xi is mapped to a yi, or sorry, x1 has a y1 of 1, and then every xi from 2 up to d plus 1 has a yi that's 0. And basically we create this polynomial, which is going to be x minus 2 times x minus 3, and we put that on top and we divide it by that same polynomial evaluated at 1 for that. So yeah, that essentially means that the x minus 2 times x minus 3 polynomial gets divided by 2. And that becomes p of x. And you can sort of determine that that polynomial actually travels through all of these points, 1, 1, 2, 0, and 3, 0. So the next step is to generalize this, and the first step in doing that is realizing that x1 can actually be any xi. And we're going to create this expression, delta xi, which is going to be basically this, but we're going to do it from the point of view of a particular xi. So it's going to be the product of x minus all other x's, not xi, divided by the product of x of I minus all of the other x's. So this is an important thing to remember, what delta xi is, and then I think the next important thing to remember is what p of x equals. And that is basically the sum of all the delta xi's times their corresponding yi's. So as you can see, p of x is degree d because it is the sum of degree d polynomials. And yeah, as we saw from here, this is a q of x is a polynomial of degree d. Give me 1 second. Right, so basically we know that p of x is of degree d because of the sum of degree d polynomials, and we will find out that if we evaluate every point, we're going to get its corresponding output. Yeah, because the way this is set up, as soon as we input x of I, it's going to reduce out all of the other terms, and we can actually see this with an example. So we're going to use some slightly different points. We're going to construct a degree 2 polynomial, and we're going to create the delta i's first. So if we remember, the delta I is on top the product of x minus all x's that are not xi. So since we're dealing with delta 1, then we're not going to have x1. We're going to have x minus x2 and x minus x3, which happen to correspond to 2 and 3. Then on the bottom, we're going to have the same thing, except we're going to pass in x1. Okay, and that's going to give us this polynomial right here, and we're going to repeat the process for delta 2, which is going to give us this, and so on. Then from here, all we have to do to obtain p of x, if we reference this equation, is to multiply each of these delta x polynomials by their corresponding y values. So for example, delta 1 of x will be multiplied by 1, delta 2 of x will be multiplied by 2, and we can sort of see that here. And this will be the resulting polynomial that will pass through all of these points. Okay, so hopefully at least the construction of the polynomial makes some sort of sense. So now we're going to go on to the proof of property 2, and just to mention it again, property 2 states that we need d+1 polynomials where each of the x values are unique in order to create a degree d polynomial, such that it passes through all of those points. So basically, we've shown that we can use Lagrange interpolation to create a polynomial p of x, but now we're going to prove that this polynomial is unique, which I've been saying, but now we're actually going to prove it. So first off, we're going to suppose for contradiction that there is a second solution. We'll just call it q of x in this case. So that means that r of x, you can think of it sort of like as the remainder, is going to be equal to p of x minus q of x, where r of x is some non-zero polynomial. And by property 1, r of x could potentially have d roots. If there's two different solutions, maybe say the degree is degree 2, right? Maybe one solution has p of x being 2x squared and q of x being x squared. So if we subtract them, we would get r of x, which would be x squared, which could potentially have the same number of roots as both p of x and q of x. So this is saying that they have the same number of roots. However, if we subtract solution 1 from solution 2, and then we evaluate it at every point, we're going to see that it has a 0 at every point. So that means that there are d+1 roots, which means that this polynomial should actually have more than degree d, which it can't. So that is the contradiction there. Okay, now we're going to go over polynomial division. So as we can see from here, this kind of should look like what you do with modular arithmetic to put it into sort of the regular arithmetic space. So say we have a polynomial p of x and we divide it by q of x. Q prime is going to be the quotient, and then r of x is going to be the remainder, which must necessarily have a degree lower than p of x. Okay, so yeah, this is the example they give in the notes, and I have written out the steps, but I think it's going to be better if I just go over this solution. So I will expand this. Yeah, let's view. Okay. So yeah, so we are dividing x cubed plus x squared minus 1 by x minus 1, and we sort of do this, we handle this like we would handle regular long division. So we want to find something that will subtract out of this largest term, so we're going to multiply our divisor by, in this case, x cubed, and we do that and we get x cubed and minus x squared, and then we're just going to subtract it out of this, and so we're left with 2 of x squared. Similarly, we're going to try to get something so that the greatest term cancels out, and so we'll do that by multiplying this term by 2 of x, subtracting this out. We're going to be left with this. Again, try to take out that largest term, multiply it by 2 in this case, and we're going to be left with this remainder of 1. And as we saw, all of the terms that we multiplied our divisor by in order to subtract out a portion are kept track of up top, just as we would in regular long division. Okay. Now we're going to go over proof of property 1. And to restate it, a non-zero polynomial of degree d has at most d roots. If you remember from the uniqueness step, the reason why this was a contradiction was because we said that a degree d polynomial has d+1 roots, which is not possible because it can only have at most d roots. Right. So we're going to use these two claims to sort of put this proof together. And the first claim states that if a is a root of a polynomial p of x with degree d greater than or equal to 1, then we're going to say that x minus a times some other polynomial q of x is equal to p of x, such that q of x has a degree less than 1. Okay, and that sort of makes sense. We're going to look at this further. So, right. So, degree of q of x, it has to be less than the degree of p of x. Also, the degree of r of x is smaller than the degree of x minus a. So if we sort of think about that, yeah, we take out one root. Where was the example? Yeah, so say this is the root that we're taking out of this. This is going to be our q of x, and then this is going to be our r of x, which has a smaller degree than our x minus a. So, yeah. So, let's see. That basically means that r of x must be a constant, as we sort of illustrated above, and that means if we input a into the above equation, we should get r of x is equal to 0. So, yeah. This is a root, this becomes 0. If we evaluate a for p of x, we know that a is a root of p of x, and so 0 will come out on this side, 0 will be here, so then r of x will have to be equal to 0. Okay, and this other claim states that a polynomial p of x of degree d with distinct roots a1 through ad can be written as p of x is equal to some constant times x minus the first root all the way up to x minus the last root, where this constant is some real number. And we're going to induct on d. So let's say we have 0 roots. That means that our polynomial is just going to be equal to a constant. Okay. Basically, for the inductive hypothesis, we're just going to say that this claim holds for all d greater than or equal to 0. And we're now going to show the d plus, this works for degree d plus 1. So, let's see. By claim 1, p of x is equal to x minus, this should actually be like this. D plus 1. Yeah, p of x is going to be equal to this polynomial, where we're going to take out just one of the roots, and we're going to have this polynomial q of x, which is going to have degree d. And we know that if we evaluate p of ai, we're going to get 0, and that means that we're going to get, yeah, it's going to be 0 for every I that is not d plus 1. Let me sort of think about that. For I that is not d plus 1. Yeah, because, you know, q of x is every other root, right? Is composed of every other root. So, let's see. Yeah, because this does not equal 0, because a of I is never going to be equal to, I is never going to be equal to d plus 1, right? Because this cannot be 0, then it must be the case that this is 0. And because q of x is of degree 0, or sorry, it's not of degree 0, because it's 0 at all ai where sorry, actually, this is what I meant to say. We know that is of degree and this is going to be d. And we sort of said this before, but again, we're saying that we have a polynomial with d plus 1 distinct roots, and by property 1 that means that it is of degree d plus 1, and then we use this from claim 1 to show how q of x, it has to be of degree d, because we're taking out one of the roots from p of x. And because we know the inductive hypothesis holds on polynomials of degree d, then we're just going to show that, you know, it also holds to polynomials of degree d plus 1. Okay, so hopefully that makes sense. Okay, in finite fields, this one was fairly quick. I feel like we're going to learn a bit more about this later, but it was sort of just high level, I guess. So first off, property 1 and 2 holds in variables and coefficients that deal with complex and rational numbers. And that's because we can add, subtract, multiply, and divide as long as we're not dividing by 0. But, you know, we're dealing with modular arithmetic, and if we want to confine ourselves to the integers, then yeah, we're going to use modular arithmetic. So the way we can do that is by letting m be prime, so that every number leading up to m has an inverse mod m, right? And you know, we sort of dealt with this in Fermat's little theorem, for example. I mean, that's this is just like a very small aspect of Fermat's little theorem. It's just, you would have, basically what I'm trying to say is you would have already known this if you had learned about Fermat's little theorem. But anyways, that's not important for this. So let's take a look at this polynomial 2x plus 3 in the mod 5 space. And if we were to solve for x, we would find that x is equal to 1 mod 5, and or so, let's see. Yeah. And similarly, this other polynomial, mod 5, is also equal to 1 mod 5. And now we're going to kind of see, I guess in the next section, what that sort of looks like, because I believe I had an image here somewhere. Let me just check for it. Yeah, okay, it literally says image there, so I'm gonna assume that that is probably what I was looking for, and it is. So as you can see, mod 5, the only values that we have are 0, 1, 2, 3, and 4. And so basically we can evaluate p of x at each of these values, but their typical values that would be found in just the regular Cartesian plane are not, you know, are not there, because we can only go up to 4, so then we have to wrap around. So I'll just look at p of x, and we'll think about, you know, let's evaluate 0 through 4 at p of x. So evaluate 0, we get 3, that's just fine. Evaluate 1, we get 5. 5 mod 5 is 1, so the actual point goes down to here. And then you can sort of see how this goes on. And this is the concept of a finite field. Next, we're going to talk a little bit about counting. So question to you is, how many polynomials of degree at most 2 can you make mod m? Okay, so we're going to use degree is equal to 2 for our example. Just remember the form of the polynomial. We know that d plus 1 coefficients, each with m possibilities. So let's think about that. M plus 1. Right. So we're in the mod space of m. Let's say m is 3, right? If our degree is of degree 2, then we can think of that other polynomial that we used, which at base value is going to be, let's say, x squared plus x plus c, for example. Because we have 3 coefficients, m coefficients, d plus 1 coefficients, I mean. And we can use m different numbers, then we have m to the d plus 1 possibilities. And you can also think of this in another way, which you can think of this by remembering that p of x can be formed by taking d plus 1 pairs with distinct xi's. So this means for all the plus 1 fixed xi's, you can have m possible output y values, right? So this just goes to show that you have m to the d plus 1 possibilities. And this is going to lead to another sort of idea, which says, it takes 3 pairs with unique x's to make a polynomial of degree 2, right? So how many polynomials can you create if you remove one of those pairs? Well, if we are in the mod space, then there are m choices, right? Because we're modding by m. So we take off one of the pairs. We know what our x is supposed to be, but it can be any one of those y's that are in the mod space. And there's actually a pattern for this. Again, if we're given d plus 1 points, then we can find a polynomial of degree d such that it's unique. But if we have one less of those points, then it's possible we have m different possibilities, as we sort of showed up here. Take away one more point. Now we have m possibilities for x3, but say we took off x2. Well, for each possibility of x2, we have m possibilities for x3. So it becomes a total of m squared, all the way down to e0, where we would have m to the d plus 1 possibilities, as we talked about up here. So it's important to note that this is the case in the mod space, but what if we were just in regular integers? Well, at that point we have an infinite pool of numbers to deal with. So, if we have 2 points that form a line, but then we take 1 point away, we can choose from an infinitely large set of points to get that second point. So we have really no idea of knowing what that second point would be. And that sort of transitions into the last topic, which is about secret sharing. And I'm sort of just going to talk about the steps involved. I'm not going to go over the example because I believe in the notes they do a pretty good job of illustrating it, but basically my goal here is to hopefully make a wall of text a little bit more understandable. So the example they give is about nuclear launch codes. So imagine you are the president, okay? In the event that an attack occurs that would require the US to use nuclear power, but there's not enough time to let you, the president, know to authorize the use of that nuclear power, you're going to allow a certain number of officials access, such that if k of those officials come together, then they can determine what the launch codes are. Okay? But something that we're going to notice is that if even one less than k of those officials try to come together to determine what the launch codes are, they won't be able to do it, and they will not have any easier of a time in figuring it out than they would if they were to try to figure it out on their own. Okay? And we're going to use polynomials to kind of do this. So we're going to create a polynomial of degree k minus 1. Okay? And we're going to decide to operate over a finite set of numbers, q, where q is going to be that prime. The q is going to be a large prime number that's going to be kind of like where our mod space is. Okay? And we're going to say that p evaluated at 0 is going to be our secret. Okay? So we know that we have to give out k shares in order to create a polynomial of degree k minus 1. So what we're going to do is hand out k of those shares to k officials. And what that's going to look like is p evaluated at 1 that's going to be handed to official 1. P evaluated at 2 is going to be handed to official 2, and so on. So P of k will be handed out to official k. So in that case, if k officials come together, then they can use Lagrange interpolation to construct P of x and evaluate it at 0. So, I mean, if we remember, Lagrange interpolation used these two equations right here. And again, if k minus 1 officials came together, then as we saw in this part right here, if only this would be k minus 1 in this case. If only k minus 1 officials came together, then there would be m possible values, which is 0, could be anywhere between 0 and some very large prime q. So they're essentially shooting in the dark. They really have no way of guessing what that number is. And if you want to see an example of that, then again, I would recommend looking at the notes. But that was just sort of the understanding of it. But as far as note 8 goes, that's pretty much it. This has just been my typical walkthrough for CS70. So thanks for watching.